Welcome to Calculus. Today we will investigate integration by substitution with trigonometric and exponential integrands. We'll take a look at 4 examples. Our first example is the indefinite integral of pi sine of pi x dx. So I want to approach this one by substitution, and where I'm going to draw my attention is the angle here on the sine function. So that's pi x. So the way that I want to define pi x is as my u. I'm going to call u pi x. So then I want to decide what my du is going to be defined as. So I'll take the derivative of pi x, and that's just pi times 1 dx. And just looking at the parts that I have left, pi itself is there in the integral as a factor, and then dx is represented as well. So this example doesn't require any additional coefficients. All I need to do is define this in terms of u. So my next step is going to be to call this the integration of simply sine of u du. Again, the pi dx is here for du, and u itself is pi x. So now I'm going to integrate this simpler version that contains the u's. And so I need to think about sine of x. That's my derivative. The antiderivative to sine of x would be cosine of x. But I need to remember that actually the derivative of cosine is negative sine of x. So what I need to do is I need to include a negative on my sine of x, but since it wasn't there originally, I need a second negative on the outside of the integration. The overall sign's positive, but now it's in a negative form, so that when I integrate, this becomes negative from the outside negative 1. In fact, I should probably put that as a negative 1. So the negative 1's there, times cosine of u, which is all in order now since this is represented as negative sine of u, and then plus c. All that's left for me to do once I integrate like that is to substitute back in pi x for u. So my integral is going to be equivalent to negative cosine pi x plus c. And that completes the integration for this first trigonometric example. Our second example is also a trigonometric function set up in a ratio. We have the integration of cosecant squared of x divided by cotangent cubed of x dx. So again, we want to decide how we're going to substitute here to make this a simpler integrand. And what I'm noticing is that there's a relationship between cotangent and cosecant squared of x. Recall that the derivative of cotangent of x is negative cosecant squared of x. So that's actually how I'm going to set up my substitution at first. So u is going to be simply cotangent x. And then again, the derivative of cotangent x du is going to be negative cosecant squared of x dx. So I do notice that I've got this extra negative sign that's not included in my original integrand anywhere. So what I'm going to do here is I'm going to say that negative du is equal to negative, which is going to be positive. So I can use that when I set it up. So I want to make my substitutions, but before I do so, I need to kind of clean up this second version that I've got here. I want to call, in fact, let me back off these negative signs. I'm going to define this one in terms of dx. we'll see in a moment why we need to do that. So I'm just going to solve for dx here. Dx, if I divide across negative cosecant squared of x, that'll cancel here on the right. Negative cosecant squared of x. That'll give me another way of defining dx. And in fact, it's going to be convenient for this problem to do it in this manner. It's going to create a nice cancellation for us. So I'll write that. That's how we're defining dx. So let's make our substitutions. We've got some pieces set up here. So I'm going to start off by calling this the integration of cosecant squared of x. I didn't make any substitution for that factor in the numerator. We'll see in a moment how we'll treat that. Over, I'm calling u cotangent of x. So if I've got my denominator cotangent cubed x, I can substitute that for u to the power of 3. And then my dx, I've highlighted it here. I want to place in this whole du over negative cosecant squared of x. Now place that in there, and what we're going to see is a cancellation right away. So negative cosecant squared x, and that matches my numerator, so that's going to cancel out. And so for my substitution version, what we've got is the integration of negative, from this negative sign down below, 1 over u cubed du. And at that point, what I want to do is just integrate that with my u's. So I can also think about it as the integration of negative u to the power of negative 3 du. So we're ready to integrate. So that's going to be negative 1 from that negative sign out front. If I add 1 to negative 3, that's negative 2. So it's going to be 1 over 2. In fact, negative 1 over 2. U to the power of negative 2, and then plus c. We can simplify here by combining my coefficients. That's basically going to become positive half. And then I can substitute back in my u. So I defined u again as cotangent of x. And then plus c. And as a final version, I can write this as, oh, I forgot my power. So to the power of negative 2. So I'm going to let that descend to the denominator. This is 1 over 2 cotangent squared of x plus c. And that completes the integration for that question. So those two were trigonometric examples. Let's take a look at two examples that involve exponential integrands. Here I've got the integration of the fraction 5 minus e to the power of x divided by e to the power of 2x dx. And I want to use a similar strategy to one we'd seen earlier, where I can really distribute this denominator to the 5 in the numerator and to the minus e to the x in the numerator. So I'm going to rewrite this as two fractions. The integration of 5 over e to the power of 2x plus negative e to the power of x over e to the power of 2x dx. And from that step, what I can do is change these powers so that they're negative powers. So now this is going to be the integration of 5 e to the power of negative 2x minus e to the power. Now to combine this x above and this 2x below, remember I subtract that power. So x minus 2x is negative 1x dx. So that gives me opportunity at this point to make a substitution. In fact, what I want to do is make two substitutions. I want to really focus on this first term, and I want to call e to the, or I'm sorry, I want to call u sub 1 this power negative 2x. That means du sub 1 is going to be simply negative 2. So I need that to be 5. I see that I've got a 5 there. So the way that I could do that is multiply by 5 halves on the outside. So if I include that over here, you can see that's going to reduce down to just 5. In fact, that needs to be negative 5 halves. So we'll make a substitution for that first integration. So that's going to be the integration. I'll put the negative 5 halves out front of e to the power of u sub 1 du sub 1. Now I've called that u sub 1 because I want to make a second substitution here, and it's really with regard to this second power of e. I'm going to call u sub 2 the power here negative x, which means du sub 2 is going to be negative 1. And that's just fine because I actually have a negative 1 there already, dx. I'm going to need to make sure to put dx on both of those. So for that second piece, the way I can set that up is minus, actually, let's do it as plus, because I've taken care of the negative here in my du sub 2, e to the power of u sub 2 du sub 2. So it's a strange arrangement, but I'm treating it as two separate u values. I'm ready to integrate. In fact, I should put the integration there as well. So let's integrate that first term. So this is going to be negative 5 over 2. And then the integration of e to the u du is just e to the u sub 1. And same for my second integration. There's no factor there, so plus e to the power of u sub 2, and then plus c. So that integrates. What I need to do now is substitute back in my u values. So for this first fraction, what we've got is negative 5 halves. E to the power by u sub 1 was negative 2x, plus e to the power of u sub 2 is negative x, plus c, and that completes the integration. Our last example is another exponential with base 3. Here we want to integrate 3 to the power of x over 2 dx. The substitution I want to make for this one, again, is the power. I'm going to call u x divided by 2. So we'll find the derivative of that. So derivative of x over 2 is going to be half dx. So I need to include, there's no half coefficient in the integrand. So what I need to include is a factor of 2, which will cancel that. So I'm going to plug in dx is 2 du. So I'm ready to set up the integration. It's equivalent to the integration of 3 to the power of u du, but then I need to include the 2 as a coefficient there. So we're ready to integrate now. We need to remember how to integrate 3 to the power of u. So if that was a derivative, 3 to the power of u, and I was looking for an antiderivative, I need to remember that 3 to the power of u, its derivative is natural log of 3 times 3 to the power of u. So what I need to include out front is something that will cancel that natural log of 3. So I'll include 1 over natural log of 3. All right, we're ready to integrate. So this is going to be equal to 2 times 1 over natural log of 3 times 3 to the power of u. plus c. Once I make the integration, I'm ready to substitute back in my u, which is x over 2. So this is going to give me 2 over the natural log of 3 times 3 to the power of x over 2 plus c. And that completes the integration for this final exponential example. Thanks for joining for this investigation of integration by substitution. See you soon.